Hello everyone, myself Yukta Srinivas, pursuing my engineering in Sri Venkateshwara College of Engineering. My USN is 1VE23IS058. I'm in second year, third sem. The subject we are going to discuss in this video is Digital Design and Computer Organization. The subject code is BCS302. The title we are going to discuss in this video is BCD Counter. Let's begin the video. BCD Counter. Introduction to BCD Counter. A BCD counter counts in binary coded decimal format. It represents decimal numbers using binary values. This counter is widely used in digital electronics for display purposes. Definition of BCD. BCD stands for binary coded decimal. Each decimal digit is represented by a 4-bit binary number. For example, the decimal digit 5 is represented as 0101 in BCD. Importance of BCD counters. BCD counters simplify the conversation between decimal and binary. They are essential in applications involving decimal display. BCD counters help reduce errors in digital systems that require decimal output. Working principle of BCD counters. BCD counters increment their count in a binary coded decimal format. They reset after reaching the decimal value of 9, that is 1001 in binary. The next count after 9 is represented as 0000, starting the cycle anew. Types of BCD counters. There are two main types, synchronous and asynchronous BCD counters. Synchronous counters have all flip-flops triggered simultaneously. Asynchronous counters have flip-flops triggered in sequence, affecting speed. Synchronous BCD counter. In synchronous BCD counters, all bits change simultaneously. This design reduces propagation delay, improving speed and accuracy. Synchronous BCD counters are often used in higher speed applications. As you can see in the image, we have 4-bit synchronous down counter. Asynchronous BCD counter. Asynchronous BCD counters have a ripple effect in signal propagation. Each flip-flop is triggered by the previous one, causing delay. These counters are simpler but slower compared to synchronous types. You can see in the image. BCD counter circuit design. BCD counters are typically designed using flip-flops and logic gates. Common components include JK or D flip-flops for binary counting. Decoding circuits are used to reset the counter at 1010, that is decimal 10. Applications of BCD counters. BCD counters are extensively used in digital clocks and timers. They are crucial in calculators and electronic measuring devices. BCD counters are also used in digital displays for numeric output. Next. Advantages of BCD counters. BCD counters simplify the process of converting between binary and decimal. They provide an intuitive way to represent decimal values in electronics. Their design allows for easy integration with decimal display systems. Limitations of BCD counters. BCD counters only count from 0 to 9, which can limit their applications. They require additional circuitry for counting beyond single digits. Complexity can increase when interfacing with other digital systems. Binary counter versus BCD counter. Binary counters count in pure binary and can represent larger numbers. BCD counters are limited to decimal representations but are more user friendly. The choice between them depends on the application requirements. Implementation of BCD counters. BCD counters can be implemented using hardware or in software simulations. Common hardware implementations utilize flip-flops and logic gates. Software simulations can model BCD counting for educational purposes. Example of BCD counting. Starting from 0, a BCD counter increments as follows: 0, 1, 2, 3, 4. After reaching 9, the next count will be reset to 0. The counter will continue cycling through 0 to 9 repeatedly. Designing a BCD counter. The design requires choosing the right type of flip-flop for counting. Logic gates are needed to handle the reset conditions. A truth table helps in visualizing the counting sequence for design. BCD to decimal conversion. BCD counters can easily convert their binary output to decimal form. The conversion is straightforward due to the direct representation of decimal digits. This feature is particularly useful in digital display systems. BCD counter in real life. BCD counters are found in decimal devices like digital clocks and odometers. They are used in industrial applications for counting items. BCD technology is also implemented in various consumer electronics. Troubleshooting BCD counters. Common issues include incorrect counting and reset failures. Verifying the connections and the integrity of flip-flops can resolve problems. Logic analyzer tools can assist in diagnosing counting errors. Future of BCD counters. With advancements in digital technology, BCD counters can continue to evolve. Their integration with microcontrollers and FPGA is becoming more prevalent. Future designs may focus on reducing complexity while enhancing functionality. Conclusion. BCD counters play a significant role in digital electronic applications. Their ability to represent decimal numbers in binary form is invaluable. Understanding BCD counters is essential for anyone working in digital systems. These are some references links which I have used in my video. Thank you for watching this video. Please like, subscribe to my channel. Thank you.